Hello, my name is Vera Prytkova. I'm a research and applications scientist at CCDC, and today I will tell you how to run ultra-large docking jobs on cloud computing resources. First, let me start with introducing our software packages. At CCDC, we offer many products and services, and CSD Discovery is a collection of products created to aim in your drug discovery search. The CSD Discovery is comprised of the following products. You can do protein ligand docking using GOLD. Searching for scaffold hops and pharmacophoric patterns can be done using CSD Crossminer in order to simultaneously and interactively mine the CSD and the PDB. You can explore small molecule and protein interaction preferences using ISOSTAR, SuperStar, and full interaction maps. You can generate molecular conformations using the CSD conformer generator. Then you can flexibly align the ligands using the CSD ligand overlay. CSD Python API offers a scripting interface to CSD discovery components. Let me now move on to the ultra-large docking. By ultra-large docking, we mean screening of millions to billions of compounds. This is in the context of having very large libraries of compounds available. For example, NMN Real database has about 700 million pharma-oriented molecules. At the same time, we have available to us at a very reduced cost these large computing resources, such as clusters and cloud computing resources. They're allowing more of us to perform ultra-large virtual screens with docking methods. To make GOLD available for virtual screening, we had to overcome several challenges. The first is the challenge with input and output. There had been disk usage issues due to the requirement of unzipping of ligands for docking, as well as the disk usage issue due to many large files in the output. We also had to improve the deployment of GOLD onto common high-performance computing platforms. And the last aspect is the speed. We wanted to ensure that we're able to screen these ultra-large virtual libraries, but it had to be done within an acceptable time frame for lead generation using appropriately distributed computing resources. Let me now go into more detail on each of these aspects. The first aspect that we addressed is the input-output issue. Now, when you are using GOLD with the 2020 release, with the technology we are making available to you, there is no longer a need to unzip your ligand files prior to docking. The script that we provide for job submission allows you to have ligand files and/or directories as zipped. The output issue was addressed via a new write option called min-out, which means that you output and retain best ranking list and gold.log files. This has a significant impact in terms of the disk space usage. The second aspect was about easy cloud deployment of GOLD. We now provide you with GOLD Docker image for GOLD deployment onto a Kubernetes cluster. You can run such a cluster on many common cloud platforms, such as Azure and AWS. The CCDC also provides two new Python scripts to batch up the GOLD jobs, that is submit-tasks.py, and a script to collect the GOLD docking results from the GOLD queues, that is collect-results.py. We provide you with a comprehensive user guide on our website under Documentation and Resources, which has all the information on how to set up such a cluster and how to run GOLD jobs on it. On the licensing aspect, GOLD requires to have access to a floating license server, so this has to be a bare metal install, not a virtual machine. That's available to all of the CSD Discovery and CSD Enterprise users with the 2020 license. I will provide you now with more technical details. If you are a scientist looking to run ultra-large virtual screens, we recommend that you work closely with your IT personnel to set up for you and to manage the Kubernetes cluster. The setup will require access to two local machines. One is for submission of the gold jobs and for results collection, and the second machine is for the license server. It will also require a setup of the Kubernetes cluster in the cloud. The cluster is made up of one RabbitMQ pod and many gold worker pods. We have tested it with 1,300 gold worker pods. The setup also requires several sets of credentials, also called secrets. There are 3 such secrets for RabbitMQ pod, and there are also secrets for setting up gold worker pods and for the URL of the license server. You can also find this information in the user guide that we provided CCDC. I will now tell you how it actually works. Gold jobs are generated in your local machine and then pushed to a message queue that is running on a RabbitMQ pod in the Kubernetes cluster. As a note, this RabbitMQ comes standard from Docker Hub, but we provide the documentation how to set it up with the different set of credentials that you need for it. When you are setting up a Kubernetes cluster, the gold image for the gold worker is copied onto pod from CCDC's container image registry once, and then it's cached, and the cached copy is used for all subsequent gold worker pods. At that point, gold worker pods will be picking up jobs off the job queue and return the results to the RabbitMQ results queue. The entire time, the license server will need to be communicating with gold worker pods. This license server requires the external IP address, so it cannot be a virtual machine. It has to be accessible to the gold worker pods, and that means thinking about firewall as well. Firewall is something to think about for all local to cloud connections. In terms of the retrieval of the results, they go to the RabbitMQ results queue, and at any point it finds results, it writes them to disk in your local machine and then deletes them from the RabbitMQ. What you obtain in the end is the overarching gold results directory, which contains as many directories as you had batches of compounds. And each of these directories is given a temp name. In the job submission Python script, we choose to batch the compounds in batches of 2,000 compounds. Each of these temporary named directories has a best ranking list file that lists for each compound a compound name as well as a fitness score associated with it. And that's the result of having min out write option. The gold results directory also contains results list file that contains the overall top scoring results, the compound name, and associated fitness score. This 1000 value is customizable in collectResults.py script. And the last point, we wanted to make sure that the speed is appropriate. In order to test that, we downloaded 130 million compounds from the Zinc database. They were passed to gold queue in 50,000 batches of 2,000 compounds each. They were screened against the COMDUD target. That took about 40 hours with 1.98 seconds per ligand. To get that speed, we used a Kubernetes cluster containing 99 nodes, which are 16-core virtual machines, which provides us with 1,372 gold worker pods that had about 90% CPU load. In terms of the recommended settings, we recommend using min-out option and library screening genetic algorithm setting, which means 10% search efficiency. We found that these settings did not strongly affect the performance. Finally, in terms of the collection of results, we obtained just over 50,000 temp directories, each of which containing the best ranking list and as expected the overarching results file of top scoring 1000 compounds written in results list. We ran this on Azure and the total cost was just over £2,000. We're going to have a white paper coming out describing this virtual screen in more detail. With this, I would like to thank you for your attention.